TIFR webinar series in chemical sciences. We are fortunate to have Professor Jenny Nelson, and yesterday you heard a very basic, beautiful introduction for the photovoltaic devices, and today she's going to continue where she left yesterday. But however, just to give you idea about those people who are just joined today, we will repeat what has been said yesterday. My role here is just to give a brief introduction to this webinar series. This webinar series was conceptualized by Professor Jyotisman Dasgupta, my colleague and a good friend and collaborator. Together, we conceptualized this webinar series in the last year during pandemic, because we have been having a regular meetings to discuss our ongoing collaboration. But however, we felt that there is a need to understand a complexity of the subject with the forefront researchers in that area. And this is where we felt it, because since we are not meeting, unfortunately, physically, during pandemic, so that's the reason. And we have been very lucky and fortunate to have a fantastic series of speakers who have introduced us the topic, and our goal was to make students to participate in discussions, and hope we serve that purpose. So with this brief introduction, now I hand over this to Professor Dasgupta to formally introduce Professor Jenny Nelson today on behalf of TIFR. Yesterday it was welcome to IISc. This is unfortunately everything is virtual, but I think he will do today on behalf of TIFR. JD, please, over to you.
Yeah, thank you. Thank you, Satish. And I see a lot of familiar faces. Some of our friends, colleagues have joined. Abhishek from ISCS. Thank you, Abhishek, for joining in. I would welcome Jenny again for the second talk, and where she's going to talk about charge separation. But let's first formally introduce Professor Nelson. So Jenny actually did her bachelor's in physics from Cambridge University, and she was with Churchill College while doing that from 1980 to 1983. Then she moved to University of Bristol for her PhD in physics, which was on the topic optics of fractal clusters. And this she carried out with Professor M.V. Berry, was a pretty famous physicist at this time. And then after finishing her PhD in 3 years, she actually held a series of positions during the next almost 10 to 12 years, and ending up in Imperial College, where she is presently the professor of physics. Jenny has had a remarkable career in energy conversion and thinking about photovoltaic energy conversion, especially. Her research has been to look at new classes of materials for application in photovoltaics. Her significant achievements include developing physical models of nanostructured solar cells and discovery of the relationship between chemical or physical structure, material properties, and device functions in both dye-sensitized and organic photovoltaic materials. She has, of course, contributed hugely to this literature for almost 20 years now. And of course, for her tremendous contribution, she has had the pleasure to have lots of fellowships and awards. I would mention one that is important from the perspective, this Institute of Physics Faraday Medal, which is one of the premier awards in the UK. Jenny won this in 2016. She has been the Fellow of Royal Society and of course the Institute of Physics as well. But what is really so nice about Jenny's work that she has always taken time to explain things from conceptual basis, and she has written a book which actually is one of the most important books in device physics of solar cells. It actually is titled The Physics of Solar Cells, which is being widely used in India and abroad, everywhere actually. And there's of course a Chinese translation, as I can see, of this book as well. And this has been a very hugely popular textbook from which we all can study about solar cells and the physics of solar cells. Of course, without any questions, she did some aspects of covering that literature yesterday in the first talk. Without further ado, Jenny, I welcome you for the second part of the talk, which is understanding charge separation and recombination. Really one of the most important facets to understand in organic photovoltaics. Jenny, everything over to you.
So thank you very much, Jyotishman. Thank you, Satish. And I have to say, it's a pity for me that I don't have the chance to be in IISC one day and TFIR the next day. But in fact, I'm sitting in my office on both days. But this is how it is. I guess it's the same for everybody. Yesterday, we looked at the basics of solar photovoltaic energy conversion and what we need to turn light energy into electricity. Really starting with the idea that we need an optical gap, and we need a directionality, we need some kind of device. And then we looked at what's special and what's different about organic as opposed to inorganic semiconductors. So today, I'm going to carry on where I stopped yesterday in looking at the process of solar energy conversion, rather not so much from a device physics perspective, but from the perspective of molecular transitions. I'm going to use that approach, first of all, to just try to establish that it's exactly the same as a device approach in the simplest limit, and then extend it to evaluate to what extent we can explain different aspects of the performance of a solar cell from this kind of transition rate model. So this is a diagram that I showed yesterday, which is summarizing the processes that are going on in an organic solar cell. So we have an active layer here represented by the colors, which is a mixture of two semiconductors. And between them, they have got some optical response spectrum, and they will have an electrical gap, a sort of a lowest energy for the electrons, which will be given by the LUMO of the acceptor of the two materials, and the highest energy lowest energy for the holes, which is given by the HOMO of the donor. So we have the semiconductor in here, and it's embedded between two contacts, one of which is transparent and which have different work functions. And this difference in work function is absolutely essential to provide a direction for the photocurrent, so that the electrons will go one way and the holes will go another way whenever a pair is generated. So what goes on? We have a photon is absorbed, it generates an exciton. The exciton will live and can move over a short, say, nanosecond maximum period of time. And during that time, if it reaches an interface, then it will encounter an energetic situation where there is where there is the opportunity for the exciton to dissociate and generate a state which is a charge let's say a charge transfer state where the electron has moved mainly to another component, and the hole remains on the donor if it was a donor that was excited. And this CT state can then dissociate into independent electrons and holes, and they can move to the external circuit. So these are all the processes. And against those processes, there are loss pathways of different nature at each step. We might lose the exciton before it separates. Rather than separating into charges, it may, in the end, form a triplet which decays to ground. That's a loss pathway, and the charge pairs themselves may be combined. So I went through all of this yesterday, but I mention it again just for the benefit of anybody who might not have been there. Now, I'm describing this as a kind of a series of processes, and there's a sort of spatial cartoon up here. But at the same time, it's useful and often necessary to think about this in terms of the free energy of the states involved in the process. So we have we start off with an excited state, and during the exciton dissociation process, we normally will suffer a loss in free energy to generate a charge transfer state, and then that will may lose, it may, well, we don't, this is a question, of course, but that proceeds to a more separated state. In the end, these steps are downhill in terms of free energy, and finally the charges are extracted in an external circuit. And this is our state picture, and it's useful because we can also think about what are the size of the losses that we encounter at each stage, and of course we want to minimize those to maximize the power conversion efficiency. Now, as I mentioned yesterday, some of these steps are exactly what happens in a typical solar cell. You have light absorption, you have charge transport to the contacts and charge recombination along the way. But there are other aspects of this which are not so easily treated with a device model, and they really concern these excited states and what's happening at the interface. And that's what I'm going to try to focus on today. So we can look at the whole process of photovoltaic energy conversion really in terms of 3 steps: the light absorption step, the charge transfer step, and a final kind of charge collection step. And quite often in the field of organic photovoltaics, we use a molecular orbital picture where we represent the energies that the electron and hole would have in terms of the HOMO and LUMO orbitals of the donor and acceptor component. And that sort of visualizes quite well what is the energy that needs to be bridged with a photon, and also these energetic offsets, which are very important in enabling the forward processes that we want to happen. We can also represent those spatially, as I did in the previous diagram. But what I'm showing here is on the same graph, the 3 steps from a molecular orbital picture in a kind of spatial representation and with the state picture. So the light absorption is the most, the exciton is the most energetic state. We lose some free energy when we form the CT state, and then we lose some more free energy in the process of charge transport towards the contacts, and that's because charges recombine along the way, so their number density is reduced. And I'm going to be coming back to this state picture as we go through the lecture. So how do we then relate these quantities to the important characteristics of the solar cell? Well, this kind of explains why we need to think with more than one picture. So the state picture is helpful in giving us an idea of...
Sorry, Jenny, I think there's a question.
I'm sorry.
Ravi Kishore?
Yeah. Hi, Jenny.
Hello.
In the state diagram, which you show at the bottom, and you represent the potentials of the charge transfer state and the charge separated state, right?
Yeah.
So the energies of the charge separated state you have shown it below. What are the binding energies involved? You have shown the ECS to be lower than ECP.
Yeah. Well, in the end, so this is, I mean, it's a diagram. The ECS could be lower than ECT. It could be higher than ECT.
Okay.
In, you know, I mean, I think at this stage, I'm not trying to say,
okay,
these are exactly what the energies are. If the ECS was always higher than the ECT, I think the solar cells wouldn't work as well as they do.
Yeah.
It would be possible for the solar cell to work if finally the ultimate charge separated state, so that is the charges at the contacts, are lower in energy, then this can still happen. We can still go uphill. In order to establish whether that happens, we would have to do temperature dependent measurements. But for the moment, I mean, I'm not trying to use this diagram to say these are the energies, but I'm rather using, I mean, I think the ECS is not generally very much higher in energy than the ECT, or we wouldn't see the devices perform as well as they do. Exactly what the energies are is quite hard to know.
Thanks, Jane.
Is that okay for the moment?
Yeah, I think it should be fine. Yes, please go
Yes.
ahead.
Okay, thank you. So it's a state diagram, which is the thing that's going to sort of determine the voltage. This sort of thinking is determining the voltage. And to determine the current, of course, that depends on how many photons or what part of the solar spectrum was absorbed. And then it depends on the quantum efficiency, which is how many of those absorbed generated excitons finally result in charges in the external circuit. So that's the external quantum efficiency in the solar spectrum will give us that. And then the offsets at each of these steps will determine the voltage. And we're going to come back to this concept later. So it would be nice to know to what extent we could predict these characteristics of a device in terms of molecular parameters. So I'm going to focus here, and I mean, so I think for the moment, anybody who has got deep concerns about the relative energy of these different states, I mean, let me just say I'm using this diagram to illustrate the processes, and I'm not trying to make any strong statement about energies along the way. My experience and my intuitive feeling is that the processes will tend to go in a downhill direction, but there still could be some uphill steps at stages along the way. So I don't worry if you don't like where the energies are. We can certainly discuss it in questions, but for the moment, I just wanted to talk about the processes involved. So we have a process that involves an excited state, some kind of intermediate state that I'll call a charge transfer or CT state, and a charge separated state. And we could describe all of those states with a wave function, ground state, excited state, charge transfer state, and then the charge separated state. I mean, what is that? Well, when the charges are separated, then you have polaron states, one for electron and one for Hall. So as we go through this, we have each of these processes, the light absorption, the charge transfer, and ultimately charge transport. They're all basically transitions between states. And we can regard them as transitions. And in certain conditions, we can use non-adiabatic sort of transition rate theory or Marcus theory, or some variant of that, to quantify the rates of the transition. So I'll come to that a little bit more detail in the next slide.
Can I interject you just as you're building up the model? I'm sorry, just for a second. Jayashree Nagesh, Dr. Jayashree Nagesh, she has a question. There's another question quickly from one of the attendees, Varun. So Jayashree, could you just ask your question?
Yeah, yeah. Can you hear me?
Yes, sure.
Okay, so just a quick question, because I apologize if I missed it in yesterday's talk. I didn't attend. You referred to free energies in your last slide, but you know, I'm just a little confused as to how much of a role does the entropy plays, because you know, when you talk about electronic levels and all these energy levels that you're showing, these are primarily going towards internal energy, right?
Yes, that's right. So, so in the previous slide here, when I'm talking about reaching the potential, we need to think about free energies. But when we think about an individual transition, I mean, the energy here should be the free energy of the ensemble of excited states. But I'm going to think about a single transition between, ground state and an excited state, and then the statistics can be done at a later stage as you build up a model. I mean, there is a distinction. It's important.
Right.
But sometimes it's not that easy to try to show both the entropy and the electronic transition in the same diagram.
Sure. Yeah, I can sort of wait for more detail in the same. I just wanted to check if I missed something. Okay, thanks.
Okay. Jenny, I think you can go ahead. I don't see the raise of hand from the other person, so please go ahead.
Yeah. So I'm trying to suggest that we could think about this in terms of a series of transitions. And so what are the states involved? So the different states, so we have a photon absorption that we can consider a transition between ground state and final state. And when that happens, then of course the reverse process, which is a decay of the excited state, must also happen. It involves the same states, and of course there is a nice reciprocity between the rates that's already been defined by Einstein's equations over 100 years ago. We then have a process of energy transfer, where an exciton may transfer from one site to another. We have a process of charge transfer, where the exciton transfers to a charge transfer state, and we have charge separation, the transport of holes, and of course recombination, where polarons will come together to give us back a ground state. So this is kind of a sort of framework that I would suggest that we could describe the dynamic, that we could describe the system in terms of transitions between states. And just to step back a little bit towards the tool that we can use for this. So I do believe that Frank Spano dealt with this a bit in the context of excited states. But we can appeal to tools from physical chemistry to describe the rate of a process between two different states of a system when we are in the non-adiabatic limit. So that is to say, when the electronic coupling between the initial state and the final state is relatively weak. So I've given an example here where I'm looking at polaron transfer between one oligomer and another one. And in the diagram, I'm trying to indicate that the conformation or the shape of the molecule is changed. And when it's charged, it's somewhat more planar. And when it's in its ground state, it's more twisted. I mean, these angles are sort of amplified, but to give you the idea that along the way, when the transition happens, when in this case a charge transfers from one to another, or you could have a molecule become photoexcited or decay, then that transition will be accompanied by a change in the conformation or shape of the molecule and a reorganization of its dielectric environment, and that is to stabilize the molecule in its new state. So we have a kind of a potential energy surface that's describing the state of the system, where molecule one is charged and the other is neutral, and a different potential energy surface that describes the final state. And it's different in terms of nuclear coordinates because both of the molecules have changed their shape. And so both of these initial and final state possess a potential energy surface. And for the transition to happen, there is the system has to move from one happy state to another happy state, but over a barrier. And if the interaction between the two states is weak, so in other words, if the transition is slow enough, we can consider this in using a non-adiabatic framework, so basically using Fermi's golden rule using perturbation theory. And then the problem of translating that into parameters that are relevant for molecules was solved by Rudy Marcus and other people. And we will, in the high temperature limit, we can use the high temperature form of Marcus theory, where the rate is described by this formula that contains the electronic coupling between the initial and final states, J, and it also contains a quantity lambda, which we call the reorganization energy, and that quantifies the amount of energy that must be paid to twist a molecule or the molecules in the system from their final states to their initial state. So it's kind of quantifying the energetic penalty of making the transition. And this is a very useful tool. It is not always valid because we may not always be in the weak coupling regime. We may have a stronger interaction, in which case this picture wouldn't be completely valid, or things may be happening too fast. However, it's a tool, and it's quite, I'm going to try and argue that it's quite a useful tool. So if we come back to what the processes in our solar cell, these are the things that matter: photoexcitation, charge transfer, recombination, and charge transport. And in this cartoon, I'm sort of representing each of these transitions in terms of the potential energy surfaces that would be involved. And I actually, so as well as photon absorption, there's the reverse of that, which would be the exciton decay, which may happen with light emission or with not. And so this is kind of, I would propose that we could describe each of these in terms of a transition. And is that fair? Well, we could do that if we knew the nature of the states involved, and as they
Jenny,
yes.
So just if fundamental questions on this using this Marcus framework. If at heterojunction, if your gap is minimum, okay, the rate of electron transfer will reduce and your exciton population will recombine. But however, if you use this recently developed non-Fullerene cells, you see very high EQE and high, efficiency. And I think this is I guess it's an ongoing debate. I'm just putting you on spot to just see that what is your thought on that, because if we use this framework, the issue I had is it indeed this framework suggests that if the gap is minimum between the heterojunction, your rate of electron transfers will slow down.
Yep.
And I would expect exciton population will recombine more and more.
Yes.
However, by doing that, people have achieved higher efficiency. So it's a sort of challenging using this framework to define the rate of electron transfer.
Yeah. So I think there's a couple of issues here, and I mean, one is that for those processes, although the net rate of charge transfer might be slow, it's not necessarily a slow process, if that makes sense. I mean, so I think that when we have, when we think about the validity, so one of the second sort of condition here would be that the reaction should be in the weak coupling limit. Mm-hmm. And if you think about charge transport in in disordered organic solar cells, I think most of the time this is fine. If you think about photo-induced charge separation, the exciton dissociation, most of the time it's probably not fine. But yet it's quite a useful tool because the other things are so much more complicated. So then there is, then we come to the question of what do we know? And I mean, there is evidence that the charge separation slows down when this gap becomes small, the net charge separation. So if you measure spectroscopically or something, how fast does polaron appear as a function of time, it becomes slower. There's certainly cases where it is slow. I've seen it slow. And that doesn't mean that we've kind of gone to a weak coupling limit. It means that we have some, probably some strong interaction between the states. It just means that it takes quite a long time for the polaron to form out of the ensemble of sort of hybrid character states that are there. And so we do see that become slow, and we do also see recombination from the local excited state, or the exciton become stronger, or we might see, as I mentioned yesterday, that the recombination from the charge transfer state becomes brighter and more exciton-like. And then I mean, then you said, Satish, but it leads to higher efficiency. So this is the bit that I think I don't know that we know that.
I think that's
what we can say is that there isn't evidence that those configurations kill you.
Yeah.
But I'm not sure that we have enough evidence, because you need to spec. I'm not sure that we have enough evidence to say having slow transfer and having recombination from the exciton state are conditions that are associated with higher efficiency.
Yeah,
I'm not sure that we know that.
Yes. I think I agree. That part I completely agree with you. Yes. There are many hands people have raised. Actually, there
are 3 hands. I can see already.
Yes. So Ravi Kishore first. I think we'll go ahead. He raised the hand first. Ravi Kishore.
Yeah. Hi, Jenny. So your charge transport is primarily dictated by Marcus theory. What about the effect of disorder and
I'm going to come to charge transport, or I'm going to come to all of these things later.
Okay.
But maybe if your question specifically about transport, maybe we could wait.
Okay.
Yeah.
Then Pavitra.
Hi, Jenny, Pavitra here. So when you say that, hi, can you hear me?
Sure.
Yes.
Yeah. So Jenny, my question is regarding, you say that the charge transfer state becomes more brighter. It's more like exciton-like. Do you mean to say that their photoluminescence quantum value increases? And do you have any evidence from the electroluminescence measurement that the external quantum efficiency for electroluminescence also improves?
Do I have any evidence from EL that sorry, say it again, that the...
Do we have any evidence that you say that it becomes more bright?
No, this is just the last sentence. It's about the evidence.
Yeah, so we don't have any external EL measurement on these kind of cells that would suggest that the electroluminescence quantum yield also improves.
So we see the electroluminescence become much brighter. Now, it's actually was quite hard for us to measure electroluminescence quantum efficiency. So I can't tell you. I mean, the quantum efficiency is low for sure. We can see that when we have a system of states where we change the offset through some small change chemical structure of the donor or the acceptor, that when the levels get closer together, that our electroluminescence gets much brighter. We can see that through the magnitude of the luminescence in a measurement on samples that are as similar as we can make them, but nevertheless we're not measuring we can see that they're brighter. They're brighter in PL, they're brighter in EL. And the other thing, the other evidence that we have is you see a change in the shape of the electroluminescent spectrum, where there is much more emission from states that look very much like the state of the acceptor alone. Usually that's the lower energy one.
Yeah. Yeah, I mean, it's more like the donor or one of this polymer, emitter, not like the really the broad one generally you see from charge transfer states, right?
Well, as the offset becomes smaller, it becomes harder to distinguish the charge transfer state.
Right.
Yeah, and so if you, I mean, you can work on that when you try to drive the electroluminescence, varying the current. So if you can see a change in the shape of the spectrum as you change the current, that may be an indication of filling, if you like. A CT state will generally decay more slowly to ground, and so if you drive the EL experiment harder, then you should see a greater contribution from the local exciton state than the CT state. But sometimes they're so close together that you don't see that, and they may even be hybridized, but they are definitely brighter.
Can I have one additional quick question? So if it becomes brighter, then what suppresses this non-radiative recombination across the interface? Because the materials they're supposed to be the same, right? So what suppresses the non-radiative recombination then?
Well, I mean, so the important thing, one of the things is when it may not be that the non-radiative recombination has got slower. It may just be that the radiative recombination has got faster. And if the radiative recombination gets faster, then your non-radiative loss, which is defined as the fraction of recombination which is non-radiative, or the logarithm of that, then that has improved. And so the device has become closer to the radiative limit. So in terms of kind of ideality of the solar cell, if you can improve if you enhance the radiative recombination, you brought it closer to the limit. So you don't necessarily have to have reduced the non-radiative recombination at the same time. But one of the sort of the difficulties of this is that whenever you do this sort of moving the offset, then you're generally changing the energy of the CT state. And when you change the energy of the CT state, that changes the non-radiative recombination through the energy gap law, as a rule. But I don't know that we necessarily need to have changed the non-radiative recombination in another way to change the radiative efficiency.
Yes, thanks, Jenny.
Yeah, Sai Santosh.
Hi. This is an offshoot of the question asked by Professor Satish. Now we are talking about this, shift in the CT state and using the Marcus theory framework for the recent material systems. Now, can we extend this and understand the very less energy loss which we observed recently using this?
Yeah, I mean, some of these questions are kind of relating to things that will come up.
I see. Yeah, because we are just figuring out like how the hybridization of the states would modify this kind of framework.
Yeah. So I think So I mean, is there? Do you have a? I mean, is there a specific question?
No. I'm just curious about this energy loss, like how in the neon filtering case, and how we are using this Marcus theory framework for that. Yeah, that's the main thing.
Yeah. So I mean, I'll try to give it a short answer to that, which is that, I mean, we did study this, and I don't have this in my lecture, but we have a paper from 2019 in JAX with Fleur and Eisner as the first author, where we studied the hybridization. But in that paper, we have a model where we basically borrow what was done, by physical chemists, by brilliant physical chemists of 30 years ago, to sort of show how we could combine the two hybridized states and calculate the impact on the oscillator strength from the degree of hybridization. And once you have that, you can then include it in a model of a recombination through the CT state. So it's, I mean, I wasn't sure to how much, I mean, there's quite a lot to cover, I guess.
Yeah, I mean, probably I have asked too many things in this one short question. I mean, I will listen to your entire talk and we'll take it up later at the end of this talk.
Yeah, please, yeah.
Thank you.
Okay, I'll carry on then if there are no more hands.
Please carry on.
All right. Right. So when can we use this approach? In certain conditions. So we need to be in weak coupling. We need to have information about energies of states, the reorganization energy, and in real life, our systems are likely to be disordered. So we should have a way to include that. And so I'm going to go on and have a look at that. But before I go there, I want to sort of make a small diversion. So we've been talking actually implicitly through some of the questions that were just asked about this issue of the radiative limit. And the solar cell, the efficiency of a solar cell is fundamentally limited by thermodynamics and by the sun. So the sun presents a certain spectrum, and we can convert because when we do photovoltaic energy conversion, we typically work with a single band gap. We could work with more. That's a different situation, but it's more complicated. We work with one band gap, and that band gap will immediately say that we lose part of the spectrum, and then for the other part of the spectrum that we can absorb, we must lose some of its energy in heat. For those photons that are very much larger in energy than the band gap. And the consequence of that is that there is a limit to the power conversion efficiency. And the most ideal situation is when the only loss process is through the radiative recombination of charge carriers. And we can work out what the radiative recombination should be directly from the absorption coefficient, from the optical property of the system. So from the absorptance of our system, we can work out from its absorptivity, we can work out its emissivity, and basically following Einstein's relations that tell us how much spontaneous emission there should be for any strength of absorption. We then can figure out what the radiative recombination rate ought to be. We do that, we get this thing called the detailed balance limit, and that sort of embodies the losses that we would consider unavoidable. I mean, there's an area of kind of our field which is aimed at trying to get past that, but I'm not trying to get past it, I'm just trying to get closer to it. That's the radiative limit. And then if you look at all of the energy in the sun as a thermodynamic picture, there will be a radiative limit, and it depends. It's represented by the white area here, and it has a maximum of about 30%. And in real life, of course, there are other loss processes, non-radiative processes as well. And they can be reduced. They can't really be completely avoided. And when you look at different semiconductor technologies for solar cells, in the best possible case, they get, they never quite get to this limit, but in some cases they get quite close. And this top star here is, of course, gallium arsenide, and that's a case of a device that was embedded in an optically controlled environment to try to maximize the use of photons inside the device. So this concept of the radiative efficiency is quite important. Now, I yesterday introduced a sort of simple picture for the performance of a solar cell device, where I say its current voltage curve is the sum of two terms, and one is a sort of constant photocurrent, and we can represent that in an electrical circuit as a current generator. You have a current going backwards, if you like, and that's in parallel with a diode current that goes forward. And the diode current is a direct result of the fact that we had to build a device with some asymmetry inbuilt. So the cost of kind of building a device with these asymmetric electrodes is that it will then pass current if you then bias it to reduce that built-in bias between it then passes current in an exponential manner, an exponentially increasing manner with increasing voltage. So it's a compromise we have to make. We've got this photocurrent and we've got a dark current, and we can work out the size of both of those terms, the photocurrent from what's absorbed by the sun above the band gap, and then the dark current in the radiative limit. You can also work it out, and in that case you work it out from the concept that your solar cell is in thermodynamic equilibrium with its environment, and it can emit radiation. In the dark, it will be emitting and absorbing radiation with the environment, and knowing what it does in the dark, you can then what it will then do when it has been biased can be described through this quite simple approach. So this is, and then from that you can work out what would be the power conversion efficiency if you put your ideal device into a circuit. You put in a resistive load and you vary the resistance, and you can find the maximum power point, just as we did yesterday. So that's all fine. Now, what I wanted to do now is to sort of make a case that actually you can reach precisely the same answer if you treat your solar cell not as this device, but as a set of transitions, where you have light absorption, light emission through spontaneous emission, and a charge transfer to another state, CT state or whatever. And we can define, so over here we were using the voltage as the to represent the potential which is generated, but we could also just represent it as mu, the chemical potential of the state. And if we have a photoexcited state, then we can define a chemical potential for that photoexcited state from the density, from its population relative to its population in equilibrium, and that potential, that's completely equivalent to the voltage on the solar cell, and it absorbs light in response to the absorptivity of the system, of the set of molecules or whatever that we have, and the solar spectrum. And in the detail balance limit, it will emit light also according to the temperature of its environment, like a black body. And so so in the limit where we consider we have light absorption, the only loss process is radiative recombination, and we could have extraction, then you have actually precisely the same mathematics, and you get precisely the same result. So my argument here would be that we can actually model the solar cell at a sort of basic level by considering it as a set of transitions. And this, of course, isn't entirely original. This idea, what I'm describing here was also developed more than 50 years ago by Robert Ross, and a couple of important papers in the 1960s, around about the same time that the Schottky-Queisser limit was being developed. And the interesting thing is, if you go back to Ross's paper, then you'll see that he treats the solar cell and the photosynthetic converter exactly the same. So basically, both of them are photochemical systems, and you can describe them in the limit as being made up of these processes: light absorption, light emission, which is required because of detail balance. There may be some additional losses as well. And then you have this sort of what you can then extract. And the relationship between the flux that you extract and the chemical potential of these excited states is what basically determines the power output of the solar cell or of the photochemical device. So then we can then introduce some non-ideal aspects, and these begin to become things that are relevant to an organic solar cell. So first thing to do would be to introduce a non-radiative pathway. And in the questions, we've just been talking about this. about one of the recent questions was about what Pabitra asked was about whether we could see a change in the sort of radiative quantum efficiency when we do something to the energy levels of the system. So our solar cell will lose some of its energy by emitting light, and then it will lose some more energy, usually a lot more, by non-radiative decay, where the excited state or the charge transfer states decay, but without emitting light. And so we can quantify a radiative efficiency to describe that process. So that's one thing that can happen. What else can happen? Well, if we introduce some intermediate step that in the process of charge separation, then there's two possible problems here. And one is that the rate of transfer of sort of excited states to that charge separated state, so this could be an analogous to the exciton dissociation step. If that is too slow, then that causes a problem. And the problem is that the quantum efficiency of charge separation gets reduced. And what happens is that your dissociation can't keep up with the separation, and the recombination then from the excited state is enhanced. And I think this probably relates to the situation that Satish was asking about in the last set of questions. So that's one limit we may fall into, one problem. Then there's another problem, which is that this intermediate state may itself be coupled to the ground, and it may allow recombination, and it may allow non-radiative recombination sort of very effectively. And if that's the case, then we lose efficiency, not because our current is limited, but because the population, the chemical potential that reaches the external circuit is compromised. And that's because we've lost some of our population through recombination. And when we work this bit into the sort of the formalism in terms of transitions, we find there's a penalty on the voltage. And you can see that here as I increase, this is increasing the rate of recombination from this intermediate state by powers of 10. And you can see how the voltage that this device delivers is reduced and reduced. And this is typically, in my opinion, I think probably in most people's opinions, this is the limit in which we're normally working for organic solar cells. We have this non-radiative recombination pathways which are leaking our chemical potential to ground. And this is the thing that we need to tackle. Now, part of my reason to introduce this idea is really to try to make the case that, so all of this is treated with, to find this, we do this with rate equations. Maybe the rate equations are not valid for these processes in a real device. However, they are quite useful in kind of indicating the different regimes that we may be working in and what things we need to pay attention to. So perhaps Marcus theory doesn't describe this rate exactly, but nevertheless, the idea that there would be a regime where this rate might matter or this rate might matter, it's something which is quite worthwhile thinking. In my opinion, it's quite worthwhile thinking about in a kind of a sort of general picture. So that was an aside. I'm going to leave it and go back to the main topic, which is to go back to this idea of the sort of trying to explain each step in the organic solar cell in terms of sort of the rate of molecular transition. So yesterday I talked about modeling devices, and the place that the point that I arrived at the end of yesterday's lecture was to say, we know these are the ways in which the organic device is different from an inorganic device. But we don't, so we know, for example, that charge, photon absorption doesn't necessarily mean a charge pair is generated we know that the recombination or diffusion coefficients are sort of influenced by chemical structure, but we don't really know exactly how. And so the point of trying to look at things from this sort of molecular picture is really to ask the question whether you could figure out what some of those unknown quantities are in the device picture are from modeling a transition. So the sorts of quantities that we could try to target would be, for example, the absorption coefficient, the mobility, recombination rate. And they could then be used in device equations. So I'm going to start with the light absorption, and so the point here would be that we can work out, if you have your, I mean, in a way, this is the simplest place to start because you just have one molecule. For example, this is a dodecamer of thiophene, and we can calculate its excited states relatively cheaply nowadays with time-dependent density functional theory. And you can then calculate when you calculate the sort of first series of excited states of the system, you can then quantify each state either in terms of its oscillator strength that describes the brightness, or in terms of the transition dipole moment. And this is just as an example for the dodecamer of thiophene. The first excited state is relatively bright, and it lies in the visible region. And then there are a series of other excited states. And the second one is represented by a star here. It's completely dark because of symmetry, because this molecule has a well-defined symmetry. And then the next state has got a symmetry that is not dipole allowed, but the initial and final states have the same symmetry. This is a plot of the natural transition orbitals of that. The hole and particle orbital for that first transition. So we can then work out an oscillator strength, and we can then use it to try to design materials which have got higher or lower absorption. And that was something that we also looked at this with polymers, and found that apart from the sort of the chemical structure of the unit that you're using, apart from the sort of the chemical structure, when you get to macromolecules like polymers, then the sort of conformation of the molecule also matters. And when you have stiffer structures, that tends to enhance the amount of oscillator strength that's coupled into the lowest state at the expense of higher lying states. But usually that's quite good for solar cells, because the density of photons increases as you go towards the infrared. So more oscillator strength in lower lying states is usually a good thing for light harvesting. So I would argue that to a fairly good extent, and we studied this actually in our group in some detail, to a fairly good extent, you could use the tools of computational chemistry to describe the optical properties of small molecules and polymers, and use that to help design things which have got a stronger absorption, or absorption in a particular regime. And I just make another comment here. So this is a set of experimental data from a published paper, but I wanted to use it to make a comment about the sort of materials that are available nowadays. So you see here on the same plot, this is showing the extinction coefficient. So that's defined as the imaginary part of the complex refractive index. And I say this, it's extinction coefficient can be defined in a lot of different ways. This is what I mean. Imaginary part of the refractive index. If we look at the sort of materials that we used to use a lot, like polythiophene, you can see that the extinction coefficient is less than 1 at the maximum, and moreover, the spectrums, these are experimental data, these are not calculations, experimental data. The spectrum is quite broad, and particularly when you look at the absorption edge for that material, it's quite broad. And now we look at the spectra for some non-fullerene acceptors that are popular nowadays and have been responsible for high efficiencies in solar cells, like ITIC, for example, and different sort of, these are different variants of ITICs and then different variants of others, the OIT TBR. But if you look, for example, at the ITIC in particular, you can see its extinction coefficient is much higher, and the edge, the absorption edge, is very sharp. And both of those things, so compared to sort of like old school photovoltaic materials, we've got something which is absorbing much further to the red, it's much brighter, and it's much sharper. And all of those things, I would say, are going to be quite important in controlling how the efficiency of solar cells has improved. So shifting to the red, it's obvious. So we have materials that absorb light efficiently in the red infrared part of the spectrum. They're going to increase current, sure. But the other thing is that this sharp edge is reflecting quite a sharp density of states. And so that means when we come back to the question that we have been quite interested in this talk, which is the question of what happens with the offset. If we look at if the density of states is sharp, then it's quite likely that if the absorption spectrum is sharp, it's quite likely that the density of states is sharp, and that there is a relatively sort of tight, the onset of the density of states coming from the LUMO side would be quite sharp, and that would sort of make the transition between something which is not favorable and favorable for charge transfer happen more sharply. So I would argue that this can be one of the conditions that has led to the observation of charge separation at smaller nominal offsets than previously. We'll come back to that. Anyway, so that was the first thing, was to consider that, and my sort of verdict on this is that the sort of rate equation picture, which is embedded in TDDFT, is not bad for describing the optical properties of small molecules and polymers. The next thing was to look at the process of charge transport. And in the process of charge transport, so this is sort of breaking it down a little bit. In our organic semiconductor, we have an assembly of molecules, and they'll be arranged in a way which is basically disordered. So they'd be close packed, they'd be well packed. There may be regimes where locally the molecules are packed in a crystalline manner, but on the whole they're not. We're not working with a single crystal. We've got molecules that they're packed together, and then when charge transport occurs, it should occur by so we generate, with light, we would generate a charge pair. So you then have an electron and polaron, but the charged state will reorganize its environment to sort of localize itself. And if our material is, if the molecules within the material are not too closely packed together and not packed into ordered a fashion, then the polaronic state will tend to localize on a molecule rather than over the whole assembly or over a region of the assembly. I qualify that in one or two slides. But we have, so we for the purpose of this kind of sort of, you know, transition sort of picture, we consider that charge is localized on one molecule and then it hops from molecule to molecule. So we'll have some assembly, and within that assembly there will be neighbors, which are weakly coupled to one another, and the charge can transfer from one neighbor to the other. And we could describe that charge transfer rate with Marcus theory, and then we could describe a process of charge transport through an assembly, and the average velocity can then give us a mobility. And so we could consider the sort of charge transport process as the kind of the collective and independent hopping motion of charges through this disordered assembly. And it will be the variation in the electronic coupling for the different things that will express itself in the mobility that you finally get out. If you have sort of wide variation in the coupling, then that will tend to slow down the transport because some charges will get trapped. And then we may also have disorder in the energies of the molecules, and they can experience that due to their environment, due to dipolar interactions, due to different degree of electronic interaction with the neighbors, and so on. So these are some of the things that control transport, how closely packed the molecules are, the order or disorder in their packing, and then the kind of the real sort of precisely what the geometry is at the contact points. And that's going to be influenced by the chemical structure of the materials as well, because depending upon where, I mean, typically our organic semiconductors are prepared with side chains to make them soluble, and the positions of the side chains and the nature of the side chains will influence how the molecules can get close to each other. So you could position side chains in such a way that molecules were better able to contact through the acceptor unit or better able to contact through the donor unit. And that strategy has been used to some extent with non-fluorine acceptors to improve their electrical electron transport. We can describe the rate sort of at each point with Marcus theory, with semi-classical treatment. And then if you're in a certain limit, if you're in an ordered case, low fluid limit, you could figure out the mobility from knowing those parameters. It's only an approximation, but you know, it's a limit that we understand. So then I think you could ask, okay, is it really true? And it's quite relevant to the question of this is semi-classical treatment. Is it really true? Is it fair to assume that the charge is localized on a single molecule?
I think that's hard to answer, because charges get localized on single. It is because there are various parameters. There's one of the issues is dihedral angle. It plays a very important role. What kind of twist you have in a chemical bond when you are designing the molecule, and that twist is essentially depends upon your side chain and depends upon, especially in pi conjugated polymer. I think the issue is what kind of environment you are providing. Actually, these polymer packs depends upon the solvent, depend upon the processing conditions. So yeah, I think that's the reason I think it's very hard in these disorder systems, whether the charge gets localized on single systems or you simply just hopping with the neighboring. I think Narayan is also there. He can also comment on that. Professor Narayan?
Yeah, I'm listening to the wonderful.
Yeah. So would you like to comment on that?
Yeah, I mean, the delocalization for a ordered pi system is expected, and hard to see it as localized. So, I mean, that is one of the motives in designing accepted system, isn't it? that you will have a reasonable delocalization, which will promote charge separation. And isn't it, Jenny?
Sure. I mean, I guess I agree that there will be definitely there will be delocalization within any macromolecule. And then we may expect some delocalization between molecules. And one argument when we think about charge transport, to some extent we have disorder on our side in terms of defending a simple picture, which is the reason being that when we think about, say, transport through if we take this image, for example, we think about transport through a disordered system, there may be regimes within which the polarone is delocalized over several molecules, but in the end, the rate is going to be limited by the slowest steps in any pathway. So steps between different, across more, unless you have a single crystal. The charge will have to move through regimes where the coupling is not strong. So there will be, and at those points, the weak coupling regime would be appropriate. But yeah, so I guess if you like, when we were talking earlier about charge separation, and I would kind of argue that in the case of charge transport, because if you think about transport like a mobility measurement or something, your charge is going across a huge distance in terms of the number of molecules it encounters. Its overall sort of average velocity is going to be rate limited by the places where the coupling was weak, rather than by the places where it was able to freely delocalize across several molecules. And so we need to understand and sort of work on, if you like, the weak coupling locations to understand it.
Yeah, but just to comment on you were talking about the persistence length in one of the slides.
Yeah.
So even the previous slide, the polymer structures, the kind of geometry the polymer adopts, it is very much depends upon the processing conditions, how you process the thin film, and you can repair the disorder or you can kick in the disorder within the system. So
yes.
It's a problem is a little bit complex to
yes.
To describe the transport or explain the transport by using Marcus model. So because of course you can pretty much say many things, but experimentally when you say take a same polymer and you cast a film with a different solvent and you start simply doing a mobility measurement, you would expect a different number. So that complexity comes from simply the kind of structure they adopted.
That's absolutely true. And I mean, the extent to which the model is any good does depend on the complexity of the system that you look at.
Yeah.
I mean, I agree with that. I think I won't. I won't waste time by adding evidence to my answer.
That's fine. But I think Ravi Kishore has raised the hand. Ravi, please.
Yes, please.
Then you can treat transport in these systems as a combination of, say, areas where the coupling is very weak versus areas where there's strong coupling, where the mobilities are much higher. A combination of both.
I mean, so you could, if you I think that's probably the right picture, and if that's the case, if the areas where the coupling is weak, or if the transport there is much slower than within the areas where the coupling is strong, then in the end, I mean, what we need to consider is kind of a network of internally strongly coupled regions which are weakly connected to each other.
Yeah.
And then it would be the distances and the rates along those directions of interaction that would control things.
And also in a polymer system like this, where the polymers are all entangled, okay, you could your there could be like a strong coupling between one polymeric chain versus the other, and also there could be areas where it's much weaker. So,
That's right.
so probably can have a combination of. So in that case, when it's much weaker, probably it's more the persistent length which decides how much that carrier travels within the polymer.
I think that's true. I would agree with that. Yeah.
And the other question is regarding what Pavitra was asking about the brightness of the CT state. So in all your modeling also, you not considered the back transfer, electron going back. You said that whenever you see that gap is reduces, and then comparable, yes. Okay, you see a brighter emission, right?
That's right.
So what about the electron going back?
I think it does, yes. I mean, it depends. I mean, whether you, I guess it's a different topic, of course, but with that picture about, and this is something, so in literature, so we have CT state, we have local exciton state, we have CT state. Yeah. When they become close, then there is evidence that this formation of a charge becomes slow. I can't say it happens in every single case, but I know there's some evidence in some cases it does. Okay. And then does that become slow because you've got forward and back competing better and better with each other, rather than having something which is strongly forward driven, have something which is forward, back, and then leaking from the bright state. Then you could use that if you were using a sort of a rate equation picture, then that's how you would describe it, with a forward rate and a backward rate that were beginning to get close to each other. But when it's in those conditions, it may be that the rate equation picture just isn't valid any longer because the interactions are too strong. And we would need to use a quantum picture where we allow the excited state. You would have an excited state that would in general involve the ensemble of local excited states and charge transfer states, and that state evolves slowly over time to eventually give you the separated. So I think that if you think in terms of rate equations, then you should definitely consider going back in order to explain the small offsets. But bear in mind that the rate equation is probably not the right picture for charge separation because the coupling is too strong and the processes are too fast. Okay. The underlying processes are too fast.
But if the barrier is too small, so you could have like when you do a temperature dependence, how does it show up?
I haven't got anything in the talk about temperature dependence. There are measurements that show there is a very weak or almost negligible barrier for charge separation. But I think these I guess there's a limited amount of data showing that the activation that in some low offset systems the activation energy is low or almost negligible. So Dieter Neyer in Potsdam has done some nice work on that. I think I probably shouldn't. I think I probably don't have more to say about that at this point. I should maybe continue.
Please.
So it's kind of relevant because we were talking about. Satish raised the question about how localized are the charges, and if you like, how good is the model of hopping. And how good the model is depends on how localized the charge is. And if we sort of consider and just take something simple like PCBM as a case, and we consider what are all the charge states in that system, if we use a tight binding approach and we find the electronic coupling between fullerenes, and we can find a lot of states. And when we did that, we found the local state was delocalized over a number of molecules. When we then went further and corrected the Hamiltonian to include some polaronic localization, we then found that the state localized, but not completely. So this evidence in the case of PCBM, which is one of almost the simplest things that you could look at, we would say, well, whether or not you could consider that a single molecule, maybe, maybe not. It depends who you're trying to convince and how hard the problem is that you're doing. With C60, it definitely doesn't. With C60, it doesn't. With PCBM, it kind of localizes almost onto one. So the charges don't fully localize. So then what do you need to do? And so you then need to find better methods. And I'm just going to give one example here because I think it's something which is quite nice. So far, it's only been applied to transport in crystals, but in future, methods like this may be applied also to charge separation at interfaces as well. And this is an approach. It was by Jochen Blumberger and his group in University College London, and they found a way to solve the, so basically they're doing, they're simulating the non-adiabatic dynamics of the state in the assembly of molecules by solving, they calculate the couplings that you need in the Hamiltonian in a computationally fast way, and they find the dominant vibrations for the molecules in the crystal, and they use those to propagate the wave function with the surface hopping approach. So,
sorry. There's a question, Professor Narayan.
Yeah. So, Jenny, in the simulation, is there an electric field which is turned on to assist the hopping?
Yeah, so in this simulation, in the paper that I'm showing here, they don't have electric field. From what I remember, I don't believe they have an electric field, but they have they sort of relate the they consider diffusion, and they infer the mobility from the diffusion coefficient. I think, I'm not 100% certain. I know they think they can do electric field, but it hasn't been treated in a sophisticated manner, let's say.
Okay, thank you.
Mm-hmm. But I mean, we can check. There've been sort of several more papers since this kind of original one, and they move forward. So I mean, electric field they consider to be possible, but it wasn't essential to make this comparison between different crystals.
One more thing, Jenny, maybe we'll pick this up after the talk ends, but there has to be some substantial numbers given to also the reorganization energies of the individual states. So in some sense, the molecules itself. How much is the polaronic relaxation for all of these systems? That's also critical with respect to when you are calculating the rates of the hopping. So I think we will discuss this after you finish, but some structure as well as energetic relationship would be good to look at.
Yeah, so in this sort of simulation by the Blumberger group, you actually, they do calculate the reorganization energies of the individual molecules, and you can see the polaronic relaxation of the charge as it moves. So you kind of have a charge, it's sort of like it jumps, disperses, contracts, and then jumps again. And it's like the idea of transient localization, where you could almost consider it as kind of diffusion of delocalized states, which they themselves could be described with some kind of diffusion coefficient. So sure, we may come back to it later, but I guess it's worth mentioning this type of approach, because at the moment it can be used in transport. Transport is maybe one of the easier problems, at least if you have some molecular rather than polymer material. And later, the same approaches we hope can be used for charge separation. Okay.
There's Santosh. Santosh, you had a question. Could you just
yes. Just I wanted a clarification. Can you hear me? Yeah, I just wanted a clarification on this picture when you said 39 femtoseconds. Is it the time it takes for the excitation to move from the red spot to the blue spot? This particular figure you showed in this, what does it mean?
Yeah,
importantly,
so
the timing.
Sure. So I took. So the figure is from this paper by Samuele Giannini, and it's one image in they show what they show is the progress, that the polarons progress, and I believe you're right that the red spot is where it started, but I can't be totally certain without looking up the paper. But this is like 39 femtoseconds into. So let's say over a period of kind of order 100 femtoseconds, you can see the polaron moving around that regime. So yeah, I think that's what it means.
Okay. I just wanted a clarification. That is okay. Thank you.
Okay.
Ravi Kishore, I would request we take all questions after she finishes right now. Is that Ravi? Is that okay?
Yeah, I think that's
Yeah,
please go ahead.
Okay. So I was going to then talk about charge separation. And I mean, I get Jyotishman and Satish, maybe I could just rely on you to stop me when we
sure.
When we need to stop.
Please finish. We will. Yeah, no problem.
I will try.
Yeah.
Okay, fine. Yeah.
Process of charge separation. Okay. And I've now included a kind of a charge separated state, because the whole picture of charge separation, we need to, and of course it's been referred to many times in the process of questions. And we need to not only generate a CT state, but we need to then complete the process and separate it. So then I'm going to sort of give what, if we sort of wheel back, 20 years or something like that. What was the perspective? What was the perspective on this? So perspective, and this is sort of now thinking just in terms of the enthalpy of the state. We have an exciton. We then dissociate the exciton by means of a second molecule whose electron affinity is higher. Electron transfers, you have a state which is lower energy. And then if you kind of do a simple physical calculation, so you've now got an electron and a hole, they might be 1 nanometer apart, they might be in a medium, which has got a dielectric constant of 3, we want to get them apart. How are we going to do that? And if we just consider the energies of these kind of individual states, this particular state, that will almost definitely be uphill, and it may be something like several tenths of an electron volt. And yet, people make solar cells, they measure quantum efficiency, they can get quantum efficiency close to 100%. So charges are getting out. How is it happening? And then that stimulated a huge amount of interest. And one of the sort of most basic things to say at this point is that this picture is wrong, in the sense that I've only considered one possible way of separating the charges. But in fact, there are many. We're in a 3-dimensional solid, and there are many ways for any charge pair. There are many ways of separating them, and that kind of abundance of separated states relative to CT states is going to push down the free energy of the charge separated state relative to the charge transfer state. And that's definitely something that contributes, and we can make some estimate of how much it contributes, but I don't know if we can do that well enough. So with this traditional view, I then go back to some older reports in literature. And there was a view that you needed a kind of free energetic driving force of some tenths of an electron volt to separate charges. And this is some data actually from my colleague James Durrant's group. So this is a type of thing that they've done quite a lot of, where they use transient spectroscopy to look at the density of polarons, and then they compare that with an estimate of the energy they think between the initial state and the charge separated state. by using the ionization potentials of the materials involved, and they could see a trend. And so it's suggesting that that if you take the first data, it's suggesting you need to have a really big offset in order to have efficient polaron generation. But then new families of materials appeared in which this didn't need to be so high, or the effect wasn't so strong. But there's a kind of, generally speaking, there was an observation that not taking the nominal energy difference between the exciton and the charge separated state, the generation of polarons would become less efficient, or fewer polarons would be generated as that energy gap get less. Another piece of data, and this is from René Janssen's group, and they actually use a different metric. They measure the quantum efficiency for photocurrent generation, its maximum value, as a function of the energy gap of the material system, the sort of absorption onset of the material system, less the VOC. And they see, again, a trend with this dying as this gap becomes small. So this is kind of this sort of empirical evidence, and it also fits in with the physical picture that, to get from here to here, you need some kind of energy gap. And how exactly you get from here to here is still a bit of a mystery, but that's kind of the picture, that to separate the charges, you need to pay something with energy. And so there's that data. Then more recently, with non-fullerene acceptors, there are other data that don't say the same thing. So to go back to that graph, the kind of this very nice collection of data from René Janssen's group, there's a trend. Now, if we look for the same type of trend in current data that includes non-fullerene acceptors, we now find it quite hard to see that trend. Of course, there's a lot of scatter, but it's not obvious from this data set that there is a trend saying that as this offset here becomes small, maybe we need to go smaller to find it, but from available data, they don't show that trend. So it seems that this sort of nominal energetic offset, we can't rely on it as being the important thing. And it seems that the charges are able to separate even without a driving force. This view is put forward. I won't say that this data prove it. There are other data that support the idea that when this energy becomes smaller, the quantum efficiency is not necessarily compromised. So what can be going on? I want to then just focus on two sort of ideas that have been published recently in literature, and I'm not particularly endorsing either of them. I mean, I think both are. I think this first one is quite interesting, and this was published earlier this year in Nature Materials, and it's quite a very nice study where the authors looked at a number of donor-acceptor heterojunctions using mainly non-fullerene acceptors, and they measure the internal quantum efficiency as a function of the offset. But the way the metric that they choose for the offset is the offset between the difference between the, so in these cases they're generally exciting the acceptor, and so that means, and then a hole needs to transfer to the donor. So that means that the important offset in terms of the materials is the difference in ionization potential between the acceptor and the donor. So that's why they plot here the difference in the ionization potential. And what they find is that as you vary the ionization potential, there is a trend, which is that the quantum efficiency, internal quantum efficiency, starts to die if that offset is less than about 0.4 eV. So that's kind of countering the view that when you get to zero offset, you still get charge separation. But in the same paper, as well as showing the the offset in ionization energy, they also show the CT state energy, and what they show is that the CT state energy doesn't follow the same trend. And they put forward the argument. I mean, they're not the only people to do this. It's also been discussed. So Denis Andrienko came up with the idea, and Dieter Neyer has also used it earlier. But the idea is that when you have at the interface between a donor and acceptor, you may have sort of permanent electrostatic interactions. And for example, if you had materials that were bearing a strong dipole and you orient them in one way or another way at the interface, that could induce a bending of the band. And this is quite a well-known effect. For example, if you have a substrate, you might deliberately try to change its work function by attaching to the surface some molecules that carry a permanent dipole, and that could shift the ionization potential up or down. So we don't have dipoles here, but the argument is that we actually do have, and always with pi conjugated materials, we have materials that bear quite a strong quadrupole. And the quadrupole charge interaction is also significant. And so they argue that at a rough interface where you've got these non-fullerene acceptors which bear quite strong quadrupole moments, at the rough interface you have a variation in the electrostatic potential as you pass through the interface, which is due to varying amounts of non-fullerene, of this quadrupole bearing non-fullerene acceptor in the mix. And that the effect of that is to give rise to a shift in energy levels at the interface that changes the energy at the interface away from what it is in the bulk. And the effect is to kind of introduce a sort of an energetic gradient or driving force that assists the charge pair to separate. So the graph here, the diagram here is kind of showing how things would be with and without the enhanced quadrupole moment. And the effect of the enhanced quadrupole moment is to bend the bands closer at the interface so that you have in fact a smaller offset at the moment of the interface. But if you consider the offset between the materials in the bulk, it's still quite significant. So this is an argument that they put forward, and they support it with some other calculations. And I think, so there's other data in literature that suggests this can be going on. And so in terms of our kind of, sort of state picture, what does it mean? Well, it would mean that depending upon these electrostatic interactions, the energy of the CT state, that is the state that's localized directly on the interface, may vary, and it may be higher in energy, but nevertheless, the charge separated state is not affected. So you could have a situation where the CT state, as probed spectroscopically, appears to be close in energy to the local exciton state, but that doesn't mean that the barrier, that the offset for charge separation to the charge separated state has become negligible. It may just mean that the division of energy between the local exciton and the charge separated state has changed so that the CT state is closer to the exciton and further from the charge separated state. So I think this idea is quite interesting. I also have some question about it as to why should this electrostatic offset always go the same way. We don't necessarily know how the molecules align at the interface. So that's one idea. Then there's another idea that appeared last year in Nature Energy. First author was Klassen, and there was Christoph Rabeck and others involved in this. And they made a different study, and they were actually looking, they looked at internal quantum efficiency and also looked at non-radiative voltage losses, but they make an argument using a model like the one which is shown below, that the most important thing is the lifetime of the local exciton state, and that kind of drives everything else. So the more emissive, the more radiatively efficient this state is, then the higher the efficiency of the overall system would be. And that certainly invokes this idea that the local exciton state can be repopulated from the CT state. That's a key part of their model. But one of the problems with this is that they don't consider, whilst you have back transfer between local exciton and CT state, they actually have a unidirectional CT to CS transfer, and this is, of course, a potential problem. But these are some different ideas, and this is still based on the rate equation approach. I included these data here just to sort of partly in response to a question yesterday about hybridization, which is just to say that when we get to this kind of low offset situation, it's very likely that our states have hybridized. And in our own work, so this is a reference to a paper I mentioned earlier, where we had a model. We show how to include this hybridization in the calculation of the voltage of the radiative losses. And at the same time, I've got some data. This is from Feng Gao and Artem Bakulin's work a couple of years ago, where they measured spectroscopically the rate of appearance of the polaron, and they were able to show that in very low offset systems, the polaron appears slowly. So I mean, I mean, what I believe is that when the offset becomes small, we then have a situation where states hybridize, and what we observe is probably better described through a treatment where we can evolve the excited state with the quantum model, and in that case, the local thermodynamics are, for the first moments of transfer, less important than the interactions between the states. So to sort of try to support that, I just make this reference to a kind of approach that can be used. So this I took a diagram from a paper of Eric Bittner and Carlos Silva about 6-7 years ago, and they I mean, several different groups have done the same thing, but they basically build up a kind of a Hamiltonian that supports both excitons and charge separated states, and they could show when they calculate all of the states for a kind of a donor acceptor interface, that the sheer abundance of charge separated states is assisting the process of charge separation. And when we look at the kind of the evolution of the, so there are a number of kind of, you know, polaron pair states, but there are also many polaron states and exciton states that are talking to each other in terms of the sort of the closeness of their energies, and the kind of the abundance of these states is one of the things which is driving the separation. So that the picture that we should use to think about charge separation is probably not as in as in some of the other models, rather not thinking about you know, electron here, electron there, but rather we have, over a limited period of time, a delocalized and continuously evolving excited state, which is, you know, connected to many different and extended charge separated states. And we need to find the tools to properly model that process. And more importantly, or equally importantly, we need to find experimental systems where we can pin down the number of unknowns so that we can properly understand things. So I would say we need to go beyond the semi-classical or thermodynamic models to really understand the process. So I had a last section on recombination. I have a feeling it may be too much for the time we have available. Yeah,
we can do it.
So it was just about, and I mean, to some extent, I have referred to different things along the way, but it's really about how we measure recombination. We measure the radiative bit, the non-radiative bit, and then with those measurements, we can quantify the non-radiative loss in terms of a voltage difference. And that voltage difference is generally higher for organic solar cells than it is for others. And how do we fix it? So we can use a transition rate model for that. And it's not bad, but the place where I want to come to in the end is really this, which is that so in the case of recombination, maybe I'll just say this, Satish, and then I'm finished, because it makes a connection with yesterday.
No problem.
So yesterday I talked about devices. Today I'm talking about transitions. Okay, can these two be married? The bit that I just missed, I was talking about how we can describe the recombination rate with the transition rate model, and we can then use it to pull out, this is going to be the size of the non-radiative loss in terms of voltage. Okay, now I'm taking a system, and this is a system which has got, we change the donor, and we have a low offset system, we have a high offset system, we have one in the middle. And we measure the solar cells, and we find, as we would expect, as you go from high offset to low offset system with the same acceptor, which is a dominant absorber, the open circuit voltage increases. Okay, we expect that. And the efficiency increases, and then it decreases, because when you get to the lowest offset system, quantum efficiency is compromised. And we can certainly rationalize that in terms of the sort of, worse driving force for charge separation. Fine. So the voltage increases, and we also measured the voltage loss for that system, and the voltage, non-radiative voltage loss, decreases. Fine. So this would be suggesting that the recombination is less in this low offset system, because the voltage loss is less. The voltage is higher, so recombination should be less. But when we measure the lifetime with an transient electrical measurement, we find the charge carrier lifetime is actually not longer in the high voltage system, but shorter. So we have a problem, which is that the sort of device measurements are telling us, and if we do spectroscopy, it's the same. Spectroscopy and device measurements tell us that in this low offset system, the lifetime of a charge carrier has been reduced, and yet when we do measure the voltage loss, we find the voltage loss has reduced. So what is the explanation? And what we found was that we actually needed then to go back to the device model to try to explain this. And we took our sort of model of what goes on at the interface, and we then inserted it into the device model. It's very easy to do it with the picture, but to do it with the equations, it basically means we add continuity equations for excitons and CT states, and we include the rate of CT state to pairs and pairs back to CT states. And what we finally find is that as we change the offset for this system, that has an impact on these rates of dissociation. As an offset gets less, dissociation rate gets weaker. However, it also has an offset, and a more profound offset, on the rate of reformation from pairs, the bimolecular reformation of pairs into CT states. And so this back transfer is actually the thing that begins to kill you when you get to the lower offset systems. And we need to try to control that. We would really need to understand what controls this back transfer rate. And so we could then finally explain things. And so my closing point on that would be, we do need the device model to finally explain the behavior of the device, even though we also need a transition model to explain what's going on with the transitions. So I think I'm going to stop there, and I'm happy to take any questions that you can fit into the time that remains.
Thank you very much. I think it was wonderful. Really comprehensive. Thank you very much for spending so much time to explaining very in detail, patiently listening your question and addressing all the queries whatever we had. I think there will be many more. JD, you want to begin?
No, I just wanted to first thank you, Jenny, for taking this time out for these two fantastic lectures. I see throughout the talk that you had a very thermodynamic picture to the entire device efficiency, sort of modeling of device efficiency and understanding of the molecular parameters. I would like to also sort of try to discuss, what do you think about the individual sort of structural dynamics that takes place while hopping, the initial photo-induced charge separation, the kinetics of the entire process, and what sort of view you have to those aspects of it, apart from these very nice thermodynamic pictures that you built in the entire 2 sessions. Can you put that into perspective also in the same framework?
Well, I suppose in 30 seconds.
Yeah, I'm sorry. no, just maybe you can give a little bit of a hint of.
Okay. I mean, if we come to the places where, so I presented the thermodynamic picture, then I tried to show how far can we go using a simple tool that's available to any physicist or physical chemist, the sort of tools of rate equations. And I think the 2 places where I got to 2 places in the talk where I'm sort of saying these transition rate models are not enough. And one is in the case of charge transport, where we could see when coupling becomes strong, and we then have delocalization of a state and an evolution in time. And the thing that will describe the evolution of that state in time is going to be precisely these structural,
the structural reaction coordinates, the reaction coordinates.
Exactly. The electron phonon coupling and those degrees of freedom. And so that I was going to say that physics, I don't know, I can say that chemistry, if you like, I don't care. those properties will determine the rates, the overall rates in some way. So they are, if we wanted to try to proceed with a kind of like thermodynamically consistent rate equation picture, we would have to base our knowledge of the rates of any transition on more detailed treatments that could be dealt with flat hole.
Absolutely. Okay, Jenny. The Marcus picture is actually sometimes overlooked. That the Marcus picture's driving force is of course important, but the reorganization and the other aspects of introducing modes that are coupled to the electron transfer, the charge transfer processes, that also becomes the Frank quantum weighted density of states become really important in certain cases, especially for the initial photo-induced electron transfer. Of course, for the hopping part, it works pretty well because all of that is in some form equilibrated in the assumptions. But I guess one of the critical steps is to sort of get to the charge separation. And once you are at charge separation, I think you can win the battle to some extent by the hopping. But that is where I think a lot of losses, as you mentioned, there were lots of losses taking place till charge separation was reached. So I think I guess both the recombination dynamics, the nuclear dynamics of recombination, and the initial charge transfer and separation. I guess that is where you should be concerned about, I guess, the structural part, and then the rest is.
I do believe so. I mean, yeah. So I mean, I gave the hopping example as an easier one, and also, you know, in that case, to some extent, the problem has been solved. So we do know.
Sure.
In the case of charge separation, I think we need similar tools, and I think it's going to be those couplings that control which transfers are preferred. They're also going to control which states are accessible. You know, if you have a whole ensemble of charge separated states, the coupling will control which ones you can actually reach before you die. Yeah.
Okay. Thank you, Jenny. I think there were questions coming from Ravi Kishore who were waiting, and Santosh.
There are a few questions in a chat box also.
Yeah.
I think this is Abhishek Mahapatra's question.
Abhishek is there and Konad is there.
Yeah. Okay. So as suggested by Vandewal, it may be the carbon-carbon chemical bound vibrational modes that contribute to the non-radiative voltage loss. And they are inherent. So how to design system to reduce those vibrational losses?
Yeah. So this is actually the part I jumped at the end because I hadn't time. But Abhishek, I completely I agree that we are when we work with our soft electronic materials, we are limited by the fact that by the fact of their vibrations. Everything is based on this carbon-carbon network, and the carbon-carbon breathing stretching modes are the ones that are involved in everything. So yes, I mean, in the work that we also this is something that will in the end have an impact. How do we get around it? Well, we have shown that when we vary other parameters of the system, for example, reorganization energies, they may be related to those modes, but not entirely controlled by them, because there's quite a big range of inner reorganization energy amongst conjugated molecules. That's something that can be played with. We also consider the oscillator strength of the CT state to be something that might be worth optimizing. So there will be that background trend, but it won't control exactly the losses. And by varying other properties of the CT state, we may be able to reduce losses without having to delete all carbon-carbon modes. The other thing is, and this is so Van der Waal himself has shown that when you work with high energy systems, you can reduce those losses massively. So I think that's also something that may be worth thinking about. I mean, you know, okay, we would have it'll come with a penalty on the so it's kind of like it's a warning not to get too deeply into the low optical gap systems that we're probably going to be compromised in what we can get out of those. But with other systems, sort of with the gaps, sort of, let's say, in the visible, I think there is room to play and to try to minimize those losses by considering particularly the factors that control reorganization energy.
Great. Okay. I think there is one
coming back to the vibrations that Jyothishman cares about.
Yeah. So that's
they are central.
Yeah. I think here is Kannad Majumdar. He's a PhD student at IISc, but he has written a very sort of, I think, Kannad, are you there? Can you please unmute and frame your question, please? You have written too many questions for me, but can you please unmute?
Hello. Can you hear me, sir?
Yeah.
Hello.
Yes.
Sure.
Yeah.
Hi. So I was wondering. So in solution, it's kind of like you were talking in detail about CT states and CA states. So in solution, it is kind of known that vibronic coupling and excited state vibrations can many times facilitate or mediate electron transfer from the initial state to the CT state. So I was wondering, from a device perspective, does these vibronic couplings and vibrations play a role? For example, suppose if I have an asymmetric DA system and there is an asymmetric vibration in the excited state, which can separate the electron and the hole, kind of. So can these be used for device making, or is just when we make devices, it's going to be a minimalistic effect?
Well, I mean, I think we would really like to be able to make devices where we could sort of control let's say the orientation and the relative geometry of the components that take part in charge transfer in such a way that we could identify which modes will be involved and then try. So, I mean, if we could design such systems, we could study them experimentally with spectroscopy and then and also with calculations, and then trying to figure out which are the dominant modes and try to, if you like, sort of reproduce the type of the type of knowledge that has been gained from solution studies of the sort that you're talking about. But in devices, we are far from that point because of the I mean, maybe we need to go back to the drawing board and kind of design the the device from the interface up, rather than design the materials, throw them together and then try to figure out what you've got. But I think the same principles should apply, allowing for, of course, the fact you have a different environment and you have more disorder and you'll have stronger electronic interactions. But I think the same principles should apply. It's just very hard to test that, and therefore it's very hard to design.
Yeah, Vivek.
Okay, thank you.
Vivek, please go ahead.
Thank you, Professor Nelson, first of all, for a very interesting and a very patient talk. So I had a question. I guess I'm trying to relate to what you said something in the previous part of the lecture, where you related the problem, or at least the motivation, to what happens in photosynthetic reaction centers. So I guess just taking analogy from there, there is a pair of very strongly coupled molecules. There are orbital overlaps. There is a known role for CT states, and then upon excitation by light, these CT states, they are formed, and then they further make charge separated states. Now, in that whole assembly, there is a role for the protein. There is a permanent dipole moment created along one of the branches of the reaction center. So that is why the charge separation only happens along one branch, and also there is no radiative recombination. So a CT state stays separated and eventually becomes a full-fledged charge separated state. So then with that in context, I guess my question is: have people explored, let's say, in assemblies where the driving forces are very less, and hypothetically, let's say we have a system that packs in a very ordered fashion. We make crystalline morphologies, at least in a small area, let's say. So have people explored the role of let's say weak permanent dipole moments on the polymer backbone in ensuring that a charge transfer state does not recombine and goes on further to become a charge separated state.
Yeah. So I think this is extremely interesting, Vivek. I mean, we are actually doing some work in this area, looking at precisely the same concepts, if you like.
Okay.
The difficulty. So I would actually dispute some of your. I mean, I think so. In the photosynthetic system, you can make it luminesce. You can make it luminesce if you block the forward transfer in a way not exactly the same as a luminescence experiment. And there is one report in literature, which is now 40 years old, so if somebody can repeat it, that would be great, where they actually measure the radiative efficiency of a photosystem using electroluminescence, and they found it was 3%, which is really big.
How much did they find? Sorry? How much did they found out it to be?
The radiative efficiency was 3%, 2.8%. So it's De Groot and Van Gorkum, 1981. Okay. And I'm not aware that the experiment was repeated. So, I mean, if you convert that, if you translate that to a solar cell, it's actually quite good given the band gap, 1.8 eV. Mm-hmm. So the difficulty, so it would be, it's a very, very appealing idea to try to sort of use some of this. So I agree with you that the the features of a photosynthetic complex. So the fact that your pigment, the chromophore positions are controlled by the protein environment and its electrostatics. That it provides many things. It reduces presumably the vibrational freedom. It provides a pathway. It provides a direction. And then you also have another feature, which is that the light harvesting plays a much bigger role, is much more efficient, if you like, harvesting of the light into a little volume where charge separation occurs rather than it happening everywhere. So it would be very nice to simulate those systems. And the problem is precisely the same as a problem that was an answer to the last question, which is it's very hard to make systems, at least for us. You know, I mean, maybe it's very hard to make systems that have got those features. And so I guess those people who are, there's some nice, you know, advances, certainly in the last year or so. There've been some very nice advances in terms of interesting systems to study, like those systems where you have maybe donor and acceptor features built into the same molecule, but still it's at quite early days compared to the way in which the high performance materials are assembled in solar cells. But I do think your idea is very, very interesting, and definitely it's a direction that we should all pay attention to.
Yeah, I think that's just to follow up comment on Vivek, what he mentioned, because this non-fullerene acceptor, indeed the shape of this molecule, it's been debated in the literature. You see that it has a dipole moment because of the kind of a shape of the molecule. Yeah, that drives the charge. I think there is a ample evidence there also. So on similar thought, where your acceptor has some dipole moment because of the kind of shape the molecule has. Yeah. Okay, good. I think there are 2 hands are up. Then we will stop after this. I think Ravi Kishore first, and then Sai Santosh.
Jenny, the simulations, you're looking at, there's no field component, right, in the simulations. So how are you getting the drift?
So if you
for the carriers.
Yeah, so if you refer to the part on charge transport, where I mentioned the work from another group, I do believe, but I mean, I don't have the paper in front of me now, but I do believe that in that paper, they inferred the mobility from the diffusion coefficient, which they measured in the simulation, and assumed that the Einstein relation is valid. And that should be okay if you don't have much disorder.
No, but there will be random diffusion, right?
Yes. But in the limit of an ordered system, when you don't have sort of anomalous diffusion effects going on, you can relate the diffusion coefficient to the mobility, at least in low field.
But what about see, the hopping also is going to be random.
Yeah, I mean, it doesn't really matter, because the directionality doesn't matter. I mean, the thing that would be implicit when you want to relate, you know, in a hopping picture, diffusion and mobility, I guess the idea that we use would be that when an electric field is applied, it would stabilize if you have a site which is like a distance A away from another site in the direction of the field, it would be stabilized by an energy of field times distance. And so if we're happy with that, so you would assume that your electric field is constant, for example, that would be an assumption. But if you're happy with that, then when you go to the low field limit for the rate of forward minus backward, it will give you a value which is proportional to the diffusion coefficient, because it's all controlled by how fast the hop goes.
Okay, so low field limit probably. Yeah. And then the other question is, what about field assisted exciton breaking or the charge separation, charge CT state, breaking of the CT state?
I don't think I've got anything very informed to say about that. I don't want to say it's not important. I think it is important. It's just not something I happen to know anything about.
Okay. So you think like a, but like how do you incorporate such things in the model? So you have to really refine the model.
Well, at the moment, I don't have a model which would incorporate those things, although I think it's a good target to have.
Yeah. Okay. Maybe you can go. Yeah. Thank you, Ravi Kishore. The last question now, I think, okay. So we have been here from, I think now Jenny is certainly very, very tired. But thank you, Jenny, for answering all the questions. So Santosh, please, can you?
Yes, Jenny, I'm sorry. Your talks should go for more than a week, I feel, because you have so much of information. And we have too many questions that we cannot ask everything in 2 talks. Let me just be brief. 2 things are bothering me. I just wanted to tell you. One is the rate equation model which you have put. Are you also considering the triplet manifold? That is point 1. The second question is, now that these non-Fulling acceptors are doing their own light harvesting because they're also extending the absorption. How about the balance between the hole transfer rate and the electron transfer rate? Would it affect the device performance?
Yeah. So two very good questions. I'm going to try to be quick as I can. So with the triplet, it's not included, but there's no reason why not. It's I think that transfer to triplet and back again is slow enough to be treated within the weak coupling limit without too many problems, and I think it will be important. My personal suspicion. So Vivek was asking about photosynthesis analogies a few minutes ago, and in the case of the photosynthetic system, the triplet is really important as a loss process. And my suspicion is, as we get closer to the limits of our organic solar cells, we may find that triplets become more of a thing we have to worry about rather than less. So it could be included in the model. At the moment, we don't have models that include triplets because we're device physicists, but as soon as our spectroscopy colleagues give us data that tell us about the triplets, we can certainly put them in, and I think they should be. I think in general they should be there. I just didn't have anything to say about them, but it's good to raise it. And then the second question was about electron and hole transfer. So of course they can both be treated, absolutely. And there is, of course, when we consider the two optically active or sort of light absorbing active components, the other thing that we need to think about apart from charge transfer is energy transfer at the interface, because in some cases we actually have, you excite the donor and the acceptor. If the acceptor is a smaller band gap and the one that's driving charge separation, the donor might do charge separation, but it could also do an energy transfer. And so if we wanted to have a complete picture of what goes on at the interface, we should have all of those things. We should have the possibility of energy transfer across the interface as well as charge transfer. And so this is, in the ideal world, we would seek to have some sort of quantum-based sort of evolution in which those processes could happen, that you had in your Hamiltonian, if you like, both excitons and charge transfer states, and all of those different events would be part of the soup. But I mean, this question, I mean, there's certainly, it's something that it can be studied already, and it can be treated with a rate equation model. But just, I guess we know that energy transfer can happen at the interface in the systems that people are working with nowadays. So don't forget that.
Okay.
Okay. Thank you.
Thank you, everyone, and thank you, Jenny. I think Satish and I, we are very grateful that you actually agreed to our invitation and spent this much of time addressing all the questions, of course, teaching us, and then addressing all the questions with regard to your 2 talks, and also sort of, in some sense, inspiring many of the principal investigators within the community in India, as well as the students. So I think that's a lot to ask, and I'm thankful that you could do that for us. we have many of us, in fact, in ISER, Pune, I was talking to one of our colleagues, Anshuman Nad. He told me that we have started a course on solar cells and for photovoltaics, and we follow with great interest the Physics of Solar Cells book by Jerry Nels. So, so thank you for doing that for many of us across the country and of course around the world. And the fact that you have been so humble in giving these lectures, there was not a point where you got aggressive with us or anything. Thank you for being such a nice person and doing this. So it's a heartfelt thank you. And I also thank all the participants, the students, the faculty members who earnestly asked questions, Ravi Kishore, then Sai Santosh, Vivek, of course, and all our people who support this program. I really would like to thank them. The ACS, again, for providing the support necessary for the Zoom interaction, especially Ajay Jha and Diksha Gupta, and both IISc faculty, the group, the department of, which Satish belongs to, Solid State Structural Chemistry Unit, and the Department of Chemical Sciences at TIFR. I thank them for the support throughout these lecture series, and that's where we end. I just wanted to say that we are going to send you something through the snail mail. You will receive soon a token of thank you. Okay.
Okay. So thank you. I look forward to that.
Yes. Sure.
Thank you very much.
Okay.
Satish? Yeah.
Thank you. I think that's what I think you all concluded very nice. I don't have to add any more.
Okay. Okay.
Thank you.
Okay. I think it's coffee time.
Yes.
Yes, it is. Yes. Thank you. Then bye-bye.
Bye.
Bye. Bye-bye. Take care.